F.2, another two questions, question number 14 and 15 for our problem-solving examples. The first example, question number 14. We use phi to represent the golden ratio. How to represent the expression 2 over phi cube plus 1. This fractional expression, we want to represent it in a more friendly form. So that is a phi plus b. Here, we want to have a and b are integers. Yeah, so that is the question. All right, so this question, we need to use the properties of golden ratio. Yeah. Mainly, we have two properties, the golden ratio. So let me just review a little bit. All right, so first, two properties we frequently use for the golden ratio. First, how do we get a golden ratio, right? When we define the golden ratio, we set up an equation, right? So that equation, it is a quadratic equation like this. That is the golden ratio equation, quadratic equation. From this equation, we have two commonly used properties. Yeah. The first one, phi squared equals phi plus 1. Second, 1 equals phi squared minus phi. Yeah. They are equivalent, yeah, but sometimes we need to use this one, sometimes we need to use another one. Yes, yeah. So here, for this question, we can use these two properties in a smart way. Yeah, you have to use in a right way, although you may have several different ways to get a solution. Yeah, but here, let me just show you one way to get a solution. All right, for the solution, yeah. First, our original form, it is a fractional form, 2 over phi cubed plus 1. We know usually the fractional form is not very friendly when we do formula manipulation. Yeah, not very convenient. Yeah. If we can convert it as, so this is a linear form, much simpler, a phi plus b. Both a and b are integers, so friendly, all right? Yeah, so for that reason, now let us try to use one of the two properties to do the transformation of the original expression. All right, so let me show you. Yeah, first, because the denominator is relatively more complicated, so we want to make the denominator as simple as possible by observation. Here you have to use your eyes to identify some special pattern. Then, based on the special patterns, you can choose the right property to use. Here, let me show you. Phi cube. Can you write phi cube as phi times phi squared? Yeah. So we commonly use this way, phi times phi squared. The reason, because you can isolate phi squared, and the phi squared appears left-hand side of our first property. All right, yeah. So for that reason, we can replace phi squared by phi plus 1. Yeah, that's the first time we use the property. Yeah. All right. Next, we like to simplify the denominator before we try to identify another pattern. All right. Yeah. Okay, yeah, yeah. All right. Look at this. After simplification, we get a phi squared plus phi plus 1. All right, yeah, okay. Then, can you identify another pattern for which we can apply one of the properties? Yeah, although there are several different ways to identify, but here I may like to group phi plus 1 because phi plus 1, that is the right-hand side of the first property. How about that? We can replace phi plus 1 by phi squared based on the first property. So that is 2 over 2 phi squared, right? Because in this way, we can cancel out that 2 to get a much simpler form, 1 over phi squared. How about that? Much simpler. If you compare 1 over phi squared and the original form, is it much better? Right? Much simpler? Yeah. But still not good enough because we still have denominator. We still have non-trivial denominator. So we still need to work on the denominator. And hopefully we want to eliminate. We want to, cancel out the denominator. Yeah. Then, now identify more pattern. All right. But this time, look at the numerator 1. 1 is the left-hand side of the second property. How about that? 1 is just the left-hand side of the second property. Can we replace 1 by phi squared minus phi, then over phi squared? Right? Yes. Although you may make that 1 more complicated, right? 1 is so simple, but now you replace 1 by phi squared minus phi. Don't worry. You do this kind of, increase the complexity, it looks like. Yeah, but you will get a benefit quickly. All right. So then, 2 terms at a numerator. So can we simplify as 1 minus 1 over phi? Right? 1 minus 1 over phi. That 1 over phi, simpler, right? But still not quite there yet. We want to do another step, simplification, to get rid of the non-trivial denominator. Yeah. Look at this. 1 again. When you see 1, can you quickly connect to the left-hand side of the second property? Yes, you can. All right. 1 minus this time another phi squared minus phi over phi. How about that? Now you can do the cancellation easily, right? All right. After cancellation, 1 minus phi minus 1. All right. Remove the parentheses, combine the like terms. What will you get? 2 minus phi, right? 2 minus phi. That's the answer. Is this the one we are looking for? A phi plus b, right? Yeah. A phi plus b. Here, a equals -1, b equals 2. Are they both integers? Yes. They are integers. Yeah. All right. Yeah. So you can see we solve it using 2 properties of the golden ratio in a pretty smart way. That is our question number 14. Next question. Question number 15. Yeah, this one. Yes. Logarithm. Yeah. We know the floor function of log base 2 of s equals a. So that value is known. All right. How to represent the expression, the floor function of log base 2 parenthesis of that as plus 3 in terms of s. Yeah, so that's what we need to do here. Okay? Yeah. But the hint, just to remind you, because this formula we learned several times, and actually in the binary search, analysis part, we derived this formula. Okay? We prove it. Yeah. But here, we need to use it. Yeah. Here, let me show you how to use it. You have to use it in a smart way. Yeah. It's not trivial. Yeah. It's not trivial. You have to do several times using this formula and get it done. Yeah. All right. Before I apply this formula, let me point out big error. All right. Yeah. Because I noticed. Yeah. So for students who work on this question before, I noticed some big mistake. All right. So let me just point out. Yeah. All right. Big error. Don't do it in this way, all right? So some students, they did like this. Log base 2, 8s plus 3. Look at how, here I do not write equal sign, okay? Because I do not feel comfortable. Those students, they put equal sign. Yeah. They wrote in this way. So I just use arrow sign. Yeah. They split like this, plus 3. They split. They pull that 3 out directly from inside the parenthesis of log base 2 function. You're not allowed to do that. We are not allowed to do that. So this is a, big mistake. All right. So that's first step. Then the second step, then, they can write in the right way. Yeah, because 8 plus s, yeah, this is correct, okay? That is correct. All right, yeah. Then, further 3 pull out plus that 3, 6 plus, this is a, right? Yeah. So they give me, 8 plus 6. Yeah. That's big mistake. All right. That's big mistake. So don't do this. All right. Never do that. Do that. All right. Now, so let me show you the correct way. The basic method. Yeah. When you see a question like this, the basic method, identify the pattern. If you are able to identify the right pattern, then you can use the formula correctly. Yeah. Just like our previous example, question number 14, we identified the right patterns for 2 properties. Sometimes left-hand side pattern, sometimes right-hand side pattern, here and there, in a smart way. Here, similarly, similar approach. All right, so let me show you the details. Our goal still floor function of log base 2 parenthesis as plus 3. All right, okay, yes. Remember our key formula, that one. Yeah. Here we have the floor function representation, right? We apply this formula the first time. We will switch to the ceiling function expression. from floor function expression to ceiling function expression. That is, we just minus 1 both sides, right? To get a ceiling function expression, ceiling function, okay? Base 2, but this whole thing plus 1. Whole thing plus 1. So what is that? AS plus 4. How about that? Minus 1, yeah? Because you need to move the plus 1 to the other side. It changes to minus 1. Or subtract 1 both sides. Yeah. Anyway, you will get a minus 1. The good thing about it, there is a common factor here. 4 times 2s plus 1. That is nice structure. We can take advantage of it. All right? Yeah. So we just, let me just write one more step. Base 2. All right? Yeah. 4 times 2s plus 1 minus 1. All right? Yeah. Another step to let you see clearly. All right. Next, now we can apply product property of logarithm. So that gives us log base 2 of 4 plus log base 2 of 2s plus 1 minus 1. How about that? Yeah. And we know log base 2 of 4, that's 2, right? That's 2. Okay? Yeah. So we do not need to copy it another time, right? Yeah, we can save some work. Yeah. We know integer can be pulled out of the ceiling function, right? Yeah, pull that 2 out of the ceiling function. So you have a 2 out. 2 minus that 1, so you have plus 1, right? So plus 1, the ceiling function of 2s plus 1. How about that? A little simpler, right? Identify the pattern another time, but this time you have the ceiling function expression. Here you have the left-hand side of the formula ceiling function expression. You want to convert it to the right-hand side floor function based expression. How about that? Okay, but when you go to the right-hand side, you see plus 1, right? Yes, plus 1, that plus 1. So you will get 1 plus, all right, so this time, floor function log base 2 of 2s, right? Plus 1. How about that? How about that? Okay, yeah. Then simplification, 1 plus that 1, you have 2, right? Yeah. Then inside the floor function, log base 2 of 2 plus log base 2 of s, right? Okay, yeah. So let me, yeah. This one equals 1, right? 2 equals 1. One integer, we can pull it out of the floor function, right? Integer, yeah. So 1 plus that 2, we get 3, right? 3. Then the remaining part, log base 2 of s, is that a, we are given, yeah, that expression is a, right? So that tells us our final expression. Now you can write a plus 3, all right? 3 plus a plus 3, doesn't matter. Both work, yeah. And that is the answer, all right? Final answer. All right. Look at the whole transformation, from one step to another step, and see if you can follow, if you can understand. All right. Try your best, try to understand. Then you can use the same idea to solve similar problems. All right, so let me stop our F.2 right here.